Welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording, the electronics reporter. Now, low power has been a feature with which marketing teams at some microcontroller suppliers have beaten each other with over the years. One claims the lowest power consumption, but explains that means in operation in the small print. The next exclaims the same, but in a non-operational sleep mode. And then you find out that upon wake up, you need to essentially restart your code because your SRAM wasn't retained. However, as we move to a world where remotely collected data is needed to make optimal decisions at system level, it's clear we need more clarity and competency around implementing power-saving microcontroller designs. Not only that, a certain amount of data, pre-processing or even artificial intelligence is needed at these points of sensing too. So to find out more about these new technologies, my experts for this episode are Scott Hanson and Carlos Morales from Ambiq Micro. Let's bring in Scott. Hi there, Scott. Good to have you on the show.
Hey, happy to be here, Stuart.
So can you tell us briefly about Ambiq and your role there?
So Ambiq is a company that's putting chips everywhere, and we're trying to make endpoints all around us intelligent. So think the billions and billions of smart things that are around us have this constant hunger to be smarter. And to your point earlier, that means we've got to have processing done at extremely low power. We specialize in that. We have a series of microprocessors that we call Apollo. We can talk more about that later. I am the CTO at the company. I'm the founder. I invented the core Spot circuit design platform. I'll tell you more about that later on, but it's my job to move that platform forward to ensure that Ambiq is always pushing the limits of what's possible in terms of power consumption. So I really look forward to talking more about that today.
That's great news because it's exactly what I want to find out more about. It's a really exciting technology, and I'm looking forward to digging down into more detail later. So thanks very much. Stay in the line because we're going to just quickly introduce your colleague Carlos as well. Hi Carlos, so what's your role at Ambiq and your area of focus?
So at Ambiq I run the AI group. So we develop, my charter I would say at this amazing company is to take what Scott just talked about, this ultra low or ludicrously low power superpower, and apply it to interesting tasks such as AI. And so that's what we do. It's a super fun task in the sense that you come into this from the big AI world thinking, okay, this microcontroller can't do much, but they're really capable devices, as you well know. And when you have when you're not so worried about the battery, you can do a lot more.
Exactly. So I'm really looking forward to getting into the AI detail because this is another key topic that we're obviously talking about a lot in the embedded industry. And then coupling that with what I think we can now term LLP, ludicrously low power, is really exciting. So hang in there. We will be coming back to you later in the show. So that brings us on to the next section of our show where we introduce our sponsor, who is Würth. Würth Electronic EEI SOS Group is a manufacturer of electronic and electromechanical components for the electronics industry and a technology company that spearheads pioneering electronic solutions. Würth Electronic ESOS is also one of the largest manufacturers of passive components and is active in 50 countries. Production sites in Europe, Asia and North America supply a growing number of customers worldwide. To learn more, visit we-online.com. That's we-online.com. Now, over the years, I've been involved in a handful of low-power embedded applications, and it's been fascinating to explore the different ways of tackling this in an embedded system. So I've got lots of questions for both Scott and Carlos. However, this show is about getting your questions answered, so hopefully you've got lots of questions prepared. You can join in the conversation by posting your questions and comments during the show. Simply use the chat function on YouTube and LinkedIn, or tweet us on X using the hashtag ElektorEI, that's ElektorEI, and we'll do our best to get you answers or guide you to resources that might help. So let's get back to Scott and welcome him to the stage here in our studio. So one of the big things that comes across on the website when we look at Ambiq as a microcontroller supplier is this term low threshold. So we all know that when we sort of study electronics, there's this threshold point, and in a traditional functionality of a transistor, when we come over the threshold, it's on, and when we come back below the threshold, it's off. What, for our viewers in simple terms, is operating transistors sub-threshold all about?
Yeah, so you've got it right. So in Digital Electronics 101, we're taught that a transistor, the fundamental building block of an IC, is a switch, and we're taught that that switch is either on or it's off. And so we use that switch to represent a digital 0 with a low voltage, maybe 0 volts, right? We represent a digital 1 with a much higher voltage, something that's well above the turn-on voltage of that switch, so that that transistor can turn fully on. And so that voltage is usually something that's 1 volt or higher. Okay, so a very, very high voltage, well above the turn-on voltage of the transistor. And so you get this really robust off and on characteristic. We can use that to build digital computers. But it turns out this kind of conventional view that we learn in Circuits 101 is overly simplistic. Okay, so a transistor, turns out, acts like a switch even when you don't exceed the turn-on voltage. There will probably be some analog designers in your audience who will know this, right? If you study analog design and treat the transistor as an analog device, in fact, it still operates like a switch, like a transistor, when you don't exceed that turn-on voltage. In Subthreshold, we take advantage of this. So instead of representing a 1 with a really high voltage, like 1 volts, we're representing it with a low voltage, like maybe 0.3 or 0.4 or 0.5 volts. And so sounds simple, right? 0 is 0 volts, a 1 is 0.3 to 0.5 volts. The benefits are tremendous. You get this huge energy reduction because you're dropping the voltage down. So it turns out that energy when you're actively switching is proportional to voltage squared. So you get a quadratic gain or a quadratic improvement in energy as you drop voltage. And so gains can be 10x or more when you start operating in this zone. When your voltage, your operating voltage, is below the turn-on voltage, the threshold voltage of the transistor, we call that subthreshold. When you're at or above the threshold voltage, maybe near the threshold voltage, we would call that near threshold. Turns out both give you enormous energy gains. At Ambiq, we build our Apollo family of microprocessors using, on the digital side, we tend to use near threshold. So we're sitting above that threshold voltage, but we get these huge energy reductions. We do a lot of analog design that is in the subthreshold range, so in the deep subthreshold range. I can talk more about that later, but bottom line is when you drop the voltage down on these chips, you can get this enormous energy savings. It comes with a whole bunch of challenges here that we can talk about in a moment, but that's the high level view.
Super. It's really helpful to understand, because that's obviously the key basis power saving element to your technology, and that's what brings me on to looking at the landscape of microcontrollers in general. So there's lots of different suppliers out there. Everybody has a low power option or an ultra low power ULP type microcontrollers. Some of those manufacturers have their own fabrication facilities. Some of them are fabless, which means the technology that's available to them depends upon their fabricator. What are the typical levers that are available to a fabless microcontroller vendor without subthreshold technology to achieve low active power or low sleep power? And I guess you can't have both always either.
Yeah. This is a big question, and I'm going to do my best to contain it so we don't have an hour lecture on our hands here. But to first order energy, or let's call it active power to start, is capacitance times voltage squared, right? So all of my levers that I can use to reduce power tend to relate to one of those two items, either the capacitance, the C. So we switch capacitance less often and less of it. And we reduce voltage, as we just talked about. So at Ambiq, we make heavy use of both of these things. Certainly our competitors try to make, I would say, use more of the capacitance reduction. obviously, as I just pointed out, dropping voltage down is a huge lever. As I mentioned before, we have this subthreshold approach, near threshold approach. We have a whole platform that we've branded as SPOT, Subthreshold Power Optimized Technologies. This is a whole set of technologies, think dozens of technologies that we've accumulated over 10 plus years of doing this to attack some of the challenges related to subthreshold and near threshold operation. What I'll comment before I get to the capacitance reduction thing, actually voltage reduction is something that has a big floor beneath us. We today at Ambiq run at very low voltages. And as we think about levers we can pull to further drive energy down, actually voltage continues to be an amazing knob. So we're looking in particular at some advancements in architectures on these chips. The MCUs of yesterday were primarily MCU cores, maybe an ARM core, a Cortex M class core with a bunch of peripherals. Well, as Carlos will talk about here in a moment, actually neural networks have become a really amazing use case. And the cool thing about neural networks is they're highly parallelizable computation. So it is a bunch of multiply accumulate operations. So MCUs of today can do 1 or 2 max per cycle. The next generation of MCUs that's designed for neural networks will be able to do 8 or more, or even hundreds or thousands of max per cycle. When that happens, you can actually run at very, very slow speeds and still achieve really high performance. So imagine an MCU that can do 1,000 max per cycle. You only need to hit maybe 1 megahertz operating frequency in order to do a gigamac every second. That's an amazing amount of compute. And the cool thing from a voltage standpoint is this. To run at 1 megahertz, I don't need a very high voltage. I don't need to run it at this, conventional 1 volt, or I don't even need to run at the half a volt ish that we run at today. I could run at 0.3 volts or 0.25 volts if I wanted and still achieve that kind of throughput. So my point is that we've not yet exhausted the potential of that voltage lever to drive power down. But you also asked about what other companies are doing and what we're doing beyond voltage. I mentioned capacitance as a big lever. When I'm looking to reduce power, a lot of what we switch is capacitances that get charged and discharged as we're doing computations. And so Moore's law has been the engine driving capacitance reduction for most companies, including us. TSMC, Samsung, all the other foundries do a fantastic job of making transistors and the wires that connect them smaller every few years, right? So Moore's law, the story about Moore's law is that it's been exhausted on the front end. So if you're building servers or phones, it's really slowing down, but it's showing no signs of slowing down in the embedded world where microcontrollers are built. So the majority of our volume at Ambiq is at 40 nanometers and 22 nanometers. We have products in development and even smaller nodes now. We can maybe come back in a future time and talk about those. But the cool thing about that is, every time I scale, I get a reduction in capacitance and energy tends to go down. There's some caveats there that we'll talk about in a minute. Actually, the bigger opportunity, though, to knock capacitance down is not just to rely on the foundries, but to look inward at the processor that you're building. For example, we spend a lot of time at Ambiq thinking about how to minimize clocking for various blocks. So most companies will run a bus fabric to communicate between a processor and a peripheral with a free running clock. Some companies might gate it on either end of an operation. At Ambiq, we're really thinking about every last clock pulse. I'm going to send the bare minimum number of clock pulses that are required to get data from point A to point B and no more. And in that way, you minimize switching inside the chip. So that's a big lever that we've exploited heavily. If you give me 30 more seconds, I want to talk briefly about sleep power. So active power is obviously really important, but you mentioned before, hey, sometimes people claim to be the best in active power, but then the sleep power is not so great. Well, Moore's law has actually been kind of counterproductive there, right? As we've gone to more advanced nodes, what we've seen is that the transistors get leakier, and you have things like gate leakage. You have subthreshold leakage that gets to be quite sizable. The fabs have done a fantastic job of creating new transistors that are less leaky. We've taken advantage of those at Ambiq. They've also done a good job of creating memory cells that consume less leakage. But at some point you're just fighting physics, right? You've got a transistor, and there's just no way to engineer the doping profiles or all the other features in a way to reduce leakage. And so that's where we at Ambiq and certainly some of our competitors have taken that challenge on. There's a lot of really interesting circuit techniques that we can deploy to drive sleep power down. One is we have a huge number of power gateable domains on our chip. So we have 40 plus power domains on the chip, all of which are individually gateable. This shocks people when we bring in new employees and kind of pull back the covers on what we built. They can't believe that we have so many power domains. That's a big deal. We've also done a lot of innovation around the memories to get the memory power down. In our latest products, we've got megabytes of memory on board, megabytes of SRAM on board, and those leak a lot, as you can imagine. So we've had to deploy some really interesting technologies to drop the voltage and save power there.
I think it's fascinating because this sort of just, I think most microcontroller manufacturers sort of go along this path of, yeah, you choose a process which is as low leakage as possible or low power as possible, and then they do some of those techniques that you were talking about, which is sort of power domains and adding extra logic in so as you can turn things off when they're not being used. But it's interesting to see how deep you've really gone into the design to make sure that power is saved with sort of, as you say, the number of clocks going through. Now, one of the things I sort of was half aware of Subthreshold before we came into contact, because there was a student working at one of my employers sort of doing some work in this low voltage area. So it was sort of knocking around, and I was searching then on the internet to sort of find out a bit more about Subthreshold. And most of the resources that you find, they sort of say that Subthreshold's been around for a long time, and as you mentioned at the beginning, sort of in analog applications like smoke detectors and comparators. But those sort of things only have a handful of transistors in them, you know. But when we're looking at microcontrollers, we're talking about tens of thousands just for a core. And then obviously the peripherals and all the interfacing with the memory as well. So what are the challenges, or what have been the challenges for you of deploying thousands of subthreshold transistors in a complex digital device?
Yeah, the biggest challenge that we have is really a trio of challenges, and it's that subthreshold and near threshold circuits have an exponential or near exponential sensitivity to manufacturing variations, to temperature variations, and to voltage variations. So, you know, if you make 1 million nominally identical transistors on a chip, they're all going to vary minutely from transistor to transistor due to the fact that we're down to, you know, atomic scales basically in constructing these transistors. That has a big effect on subthreshold, a bigger effect, it turns out, than in standard operation. And if you don't manage these sensitivities, then a chip that maybe runs at 100 megahertz under nominal conditions at room temperature might run less than 5 megahertz under worst case conditions. That's not something that a software developer can work around. You can't have a system where sometimes you run at 100, sometimes you run at 5, right? And actually even worse is there are certain circuits that just stop working in subthreshold. So memories are a great example. Where you've got really, really tiny, highly engineered devices, and if you drop the voltage down low enough, some of them just can't hold data anymore. And so the challenge in building chips with millions of transistors operating at near threshold or subthreshold is to build in adaptivity and tunability. And so we have a great deal of adaptivity and tunability in our chips. We've patented a lot of that. A lot of it's trade secret. I'll give you an example. We have internal voltage regulators. We take in an external voltage that's the standard voltage. We drop it down to something very low internally, but those regulators are constantly working to raise and lower the voltage depending on conditions. So as temperatures rise, they're changing the voltage. As they drop, they're changing voltages further. They're also being tuned chip by chip on the production line. So as we have every chip coming off the manufacturing test line, we're tuning them such that they can operate robustly at low voltage. We also, it's not just the way we trim the chips. We build our bus fabrics and our power domain hierarchy and our clocking schemes all with tolerance of variation in mind, and that's pretty challenging. And then I guess one final challenge I'll point to is that the fabs basically say to you that you shouldn't operate outside of a certain voltage zone. So we work with TSMC, the biggest third-party chip manufacturer in the world, biggest chip foundry in the world. And they provide models and they provide these transistors to us and say operate within this range. We're actually operating outside that range, right? And so the models can't necessarily be trusted, the simulation models that they give us. And the good news is TSMC has been a fantastic partner, right? They care about having the world's lowest power microprocessor manufactured in their process. They've helped us work through these issues, and so I guess what I would say is it's challenging, but if you're willing to bear or face those challenges, it's solvable.
It's incredible. One of the first projects I ever worked on was we were characterizing transistors from a foundry, and it just brings back memories of sitting there with all the equipment and doing all the tests just to find out what was going on. We were mostly focused on noise, 1 over F noise. That was our focus. But I can just see you in the lab doing all that analysis and understand exactly how challenging it is. Now, obviously, when we pull all this together and an embedded system developer then decides to go with an Ambiq microcontroller, what are their experience of it in terms of sleep and active power savings compared to what they may have experienced before? And what sort of power saving, how do you sort of construct your power saving modes? How are they presented to the developer?
So, it depends. We have 4 generations of microprocessor plus actually a timing chip, a real-time clock, and what the amount of active power savings or sleep power savings kind of depends on which family you go with. If you look at our most recent Apollo 4 family, it tends to be more focused on active power savings, and there, you're going to get anywhere from a 3, 4, 5x savings in active power to 10x or more, depending on what you use. And the cool thing that I really am excited about from our perspective is that the software should just work out of the box. So the experience for the customer is they've got a competitor's product running software on a Cortex M4. We provide our own Cortex M4 based microprocessor, Apollo 4. They port their code, and within a matter of hours or days, they've got their new code up and running, and they're measuring power that's dramatically lower than what they had. And if you look at how we've divided up our power modes to get to the second part of your question, it's a couple different modes. There's kind of 2 concepts. There's active mode and there's sleep mode. Within active mode, there is a so-called low power active mode. And this is in Apollo 4, you'd be running at 96 megahertz. And then there's also a high performance mode, active mode. And that is where you're running 192 megahertz. Think about it this way: the 96 megahertz mode is our near threshold mode, and the 192 megahertz mode is our conventional operation mode for those customers that need to temporarily burst higher to higher performance. In sleep mode, we have 2 different concepts. There's so-called sleep mode, where the clocks are gated, but the power is still applied to all the blocks. And then there's deep sleep mode, where the power to the microprocessor core is gated. We retain the contents of registers and cache and everything else through various means, but you get much lower leakage power in that state. And what's really cool, and is pretty consistent with other vendors, is every peripheral can be independently gated in the system. And so you can have a system where the core is in deep sleep, but maybe your I2S peripheral is up and running and pulling in data, or you can have an ADC that's measuring a sensor and then only waking the processor when it needs to be woken. What's really important for us is 2 things. One is that the software developers' experience be very similar to what they've experienced with other customers. I want them to be able to take the code from elsewhere, very quickly get up and running. And that's what I think they're experiencing here. The second thing is, we want the power optimizations to be kind of hidden behind a curtain, right? They shouldn't have to think about it. It should just be low power by default. And so we have a variety of functions that make that happen. It's not always easy. Power debug is one of the hardest things that you can possibly do. And so we do our best to make sure that 90% of the problems are hidden behind that curtain. They don't have to think about them.
Yeah. Again, just incredible insights into that as well. And I'm sort of wondering, obviously, the one of the advantages we have in the embedded industry today is the fact that ARM is available across a wide selection of suppliers, but then there's also sort of the hardware side as well. And I'm just wondering, bearing in mind what you said about sort of different, you know, power regulation within the chip in order to make sure, you know, the voltage that feeds all the transistors is of the right level according to complexities of the situation, such as temperature variations. Are there any sort of external hardware challenges that are sort of different in using an Ambiq microcontroller, for example, around the power supply?
No, generally it's all handled on chip. You give me 1.8 volts, I'm going to regulate it down internally. We have a built-in SIMO buck converter, so single inductor multiple output buck converter. It generates all the rails that we need internally, does so efficiently, and you're off and running. So no, the hope is that the hardware design and the software design is very similar to what you're used to.
Now, one of the big challenges as well in constructing your application is trying to understand where I'm going to get the power savings from, and depending on different devices that are on the market, sometimes it's a case of sort of waking up and into an active mode, executing code, and then sleep as much as possible. Other devices, sort of we see the recommendation that when you wake up, you should also operate at the highest possible clock speed so as you can get back to sleep mode. What sort of approach do you find works best with Ambiq devices?
Yeah, this is a long-standing debate, and I really think it shouldn't be, right? So the simple answer is you should operate at the lowest voltage that you can while still meeting your deadline. Running slower doesn't save you energy. It might save you power, right? But it doesn't save you energy. Running at lower voltage does save you energy. And so if you can go to a lower frequency and go to a lower voltage hand in hand, you should do that. If all you can do is stay at the same voltage but go to a lower frequency, generally that's not a win. And so as an example, imagine that you've got an Apollo 4 SoC. It's got a 96 megahertz mode, and imagine that you've got to run 24 a speech recognition algorithm that requires 24 million clock cycles per second. What you should do is you should run at that 96 megahertz mode that's at the low voltage near threshold operating point. If you were to run at 24 megahertz instead, but stay at that same voltage, you wouldn't really get any energy savings. So what you should do there is run at 96 megahertz, go to sleep, wake up again later, run another 24 million operations in 96 megahertz mode, go to sleep, wake back up, and duty cycle like that. So in our case, we have two DVFS points, two dynamic voltage and frequency scaling points. What you'll see in future Ambiq products actually is that we'll have a greater selection. I said earlier, I want to go to lower voltages. That's something that we'll be doing on future products. So look for that. I'll come back and talk about it again when we've got that. Our lead architect at Ambiq, he likes to talk about so-called ultra-wide range dynamic voltage scaling and frequency scaling, and that's something we really want to exploit on future Ambiq products.
Now, you've highlighted obviously the subthreshold technology and how it's deployed and used, and we've spoke mostly about that in the context of the microcontroller and a bit about the memory. Are you able to use that subthreshold technology throughout the entire microcontroller for all the peripherals? And I think on your latest Apollo 4 device, there's also an option for Bluetooth. So does it get used there as well, or are there sort of limits or maybe peripherals where it just doesn't make sense?
A little bit of both. So absolutely, we can. It's a platform. Spot is very much a platform. I can apply it to microprocessor IP that comes from a third party. We have a GPU on the latest Apollo 4 products. We apply it to that. All kinds of serial peripherals are using the near threshold operation. And if you look at the radio, you mentioned the radio in particular. Radio has a lot of pieces. You've got a transceiver front end, which is RF and analog circuits. That is, given the operating frequencies we're talking about, probably not a good use of subthreshold operation. But then you have the modem, which is a digital piece. You have baseband logic. You have a protocol stack processor. These are all great targets for near threshold. So absolutely, yes, you can apply it to the radio, but not the entire thing. What I also want to point out is we use subthreshold on the analog side too. So we've talked a lot about digital, about MCU or the CPU core and the GPU and the radio components. But on the analog side, we actually make heavy use of deep subthreshold operations. So this is pretty cool, but we run oscillators, voltage reference generators, regulators, all sorts of amplifiers, all in the subthreshold. We regularly use amplifiers with tail currents on the order of picoamps or nanoamps. I'm guessing that a lot of your listeners are used to microamps and maybe even nanoamps, but picoamps is pretty wild. Actually, just as a side story, I was in grad school at the University of Michigan developing the technology that eventually became Spot and became Ambiq. We had an entire processor that consumed a few tens of picoamps or a few tens of picowatts. And what was crazy was that in order to measure current that small, you have to get all the radios out of the room. You have to make sure that any wire is short and is shielded. You can't even move, right? I mean, if you would bump a cable, the triboelectric effect causes more than picoamps of induction in the loop there. So it's a crazy place to be operating, but we've gotten pretty good at it. And actually, some of the most exciting designs we're doing today are subthreshold analogs. So think like audio class ADCs that are capable of sampling at 48 kilohertz, but with a 10 microwatt power budget. And when you do that, you can start thinking about taking Alexa or Siri or whoever and putting it in a sticker on the wall in every room in your house and leaving it there for a year at a time. So really cool opportunities with subthreshold when you take it outside the MCU.
It's good that you sort of move there to some application spaces, because that's also what I wanted to post here as a last question before we move on to Carlos. What sort of application spaces are you seeing benefit the most from these subthreshold low power capabilities?
Well, the good news is there's a lot, right? This is in fact probably the biggest challenge we have at Ambiq is there's billions of units that we can go help every year, but which ones do we focus on? We started with a focus on consumer electronic devices, especially wearables. So consumer wearables, think smartwatches, fitness bands, analog watches, these sorts of things. And we've shipped hundreds of millions of units into that kind of space. I won't name customers, but you can go look at Google teardowns of wearables and you can get a sense of where we're being used. And what's cool there is these companies care about small package, needs to last for a week or two, and they have this constant hunger to do more, right? And so actually it turns out our value add to customers hasn't really been extending battery life. It's been more about, I'm going to give you the same battery life that you've always had, but I'm going to let you do more on that same battery life. And so as fitness bands, for example, have gone from being step trackers to monitoring heart rate to now being nearly doctor on wrist or personal trainer on wrist, we've given them the horsepower that they need to go do that. And Carlos can tell you more about that in a second. But as an extension of that, medical electronics is really in need of low power. So I'm not talking implantables. That's a great low power market, but let's stay away from that for the moment. I'm talking about wireless patient monitors, blood oxygen sensors, smart bandages, glucose meters, hearing aids. These are all things that are power constrained. They're small. They've got a small battery, and they also want to do more, right? They don't want to just sit there and do the step counting that I mentioned earlier. They want to run neural networks and do all the stuff that Carlos is going to talk about here in a moment. And look, bottom line is there's hundreds or even thousands of segments just like this. Smart home security devices, smart credit cards, sporting equipment, wireless tire pressure monitors. We're in a lot of livestock and pet tracking applications. There's all kinds of cows and dogs running around with Ambiq chips around their collar. So tons of opportunity. I'm really excited about that. So I appreciate all the questions.
Well, thanks ever so much for all those insights and the answers to the questions. We'll look forward. Stay on the line for us. We'll be back to you shortly, just after we've had a chat with Carlos to understand the AI initiatives that you're tackling and how that contributes to the Ambiq portfolio. So see you shortly.
Thanks.
So that brings us nicely on to our giveaway. Previously, we gave away 3 books from our guest and author, Chris Rose. The book was entitled Embedded Experts Guide to C. Congratulations to all of those who took part and won a copy. Your prize should have arrived in the post, and if it hasn't, please get in touch. Now, to extend our thanks to you as loyal Engineering Insights viewers, for this episode I have another book on offer. This one is AI at the Edge, and it's written by 2 Edge Impulse engineers, Daniel Sitonayaka and Jenny Plunkett. It focuses on solving real-world problems using embedded machine learning for a range of applications, from industrial and commercial to scientific. For your chance to win a copy, simply visit the link shown below and enter the keyword SPOT. That's the keyword SPOT, S-P-O-T, with your entry, and we wish you the best of luck with that. So let's get back to our guest. Carlos has been waiting here patiently in the background. Welcome back, Carlos.
Thank you.
So we've talked obviously a lot about low power, sub-threshold technology, making that possible within the Ambiq microcontroller environment. But if before the show, we were actually just talking about some of the sort of the general media's approach to discussing AI. And when we listen to the news and everything, everyone's explaining how much energy AI consumes when we're teaching ChatGPT models and things like that. What's Ambiq's approach overall to getting AI inside a microcontroller and making sure that the application has a nice long battery life?
So I think Scott was talking about this. I don't have to do much. Scott is the producer of this technology. I'm kind of the consumer in the sense that I come in as one of Ambiq's customers. I use all those facilities and all those features that Scott was just talking about. And this is a true story that I joined the company. I think I joined 2 years ago, and being a skeptical, technical person, the first thing I do is, nice slides, I'm going to go verify it myself. So I run the standard AI benchmarks, which are called MLPerf Tiny. And I thought I'd dropped to zero. I measure the power on this thing. I'm like, okay, I did the math wrong. Turns out you can't do it wrong. The benchmark suite, which is produced by a company called Ambiq, or it was back then, does all the math for you. And we were literally using less than 1/10 the power of the stat with the published numbers that I'd seen before. And if you've been in Silicon Valley or in tech for a long time, you know that 10% is amazing, right? 20% gets you a design, but 90% is unheard of. It just doesn't happen. So, for every watt that we use, our competitors use 10. That's ridiculous.
Yeah.
And so my first task after I picked my jaw off the floor and hugged my wife and said, I chose wisely. My first task was, as Scott alluded to, is how do you use this superpower? How do you apply this power advantage to real world applications? And in AI, you can use that either to extend your battery life, which is boring. You don't do anything new. Or you use it to increase your accuracy or your capabilities. So you add more classification types. You add higher accuracy because you can iterate more over the same kind of data. And we've done both.
Now, you mentioned there an interesting point. The Ambiq benchmarks are sort of well known in the embedded community for being able to compare different microcontrollers. And when we compare microcontrollers, it's not just about the core, because a lot of them are using an ARM Cortex something or other. There's other aspects of that, such as the number of wait cycles to access flash, and how the rest of the architecture is built around the core. So those have an impact on benchmarks. Are there within Ambiq sort of benchmarks which are AI or machine learning for an embedded microcontroller related? Or I know there's the ultra low power benchmarks. Is that all that's available for benchmarking in this domain?
No. There's a for AI in general. There's a industry association called MLComs, and it was established about 5 years ago when the benchmark wars in AI started. They focused on training on the data center. Most of the initial set of benchmarks were for training, and we're talking megawatts per training here. But they've moved to different segments. So there's inference at the edge, for example, things that happen on your phone. There's a set of benchmarks for that, and there is a set of benchmarks for tiny applications, what we call ML Tiny. The benchmarks that when I mentioned EMBC, that's the framework that they used to run. So the data collector, all that stuff came from MC initially. Now it's been open sourced. But the set of benchmarks is kind of industry standard. There's a keyword spotting benchmark. There's an image classification, visual wake word, which is kind of, detect that there's a person in frame, and then there's an anomaly detection. So every MCU manufacturer that's in the AI space will run those four, and not compare just latency, because it will be similar for every Cortex, but also power. So that's why MVC comes in. It's because this is it's all about joules.
Exactly. Yeah. Now, you've recently launched the Apollo 4 family. That was introduced a couple of months ago. Is there anything inside that device which helps specifically with executing AI algorithms, or in terms of sort of getting to low power AI, are you relying solely on the subthreshold technology?
So, and this is something that's really interesting about how endpoint AI, like sensor or wearable AI, differs from the rest of the world. In the rest of the world, AI dominates the power utilization. On a wrist or on a, if you're doing a smart sensor, AI does not dominate unless you have a really complex algorithm or a complex real-time algorithm. Most of the time, you are sampling data, you're pre-processing the data, and when I say most of the time, I would say order of seconds, and then you run AI for a few milliseconds. So the important thing in this space, in this domain, is to optimize everything else. Optimize your sensors, optimize your general purpose compute, your fast Fourier transform. Make sure that that's not, because when you look at the MIPS consumed, if you're doing an audio task, about half of it is fast Fourier transforms, and then what you do afterwards. So you can take AI, the inference part, you can take that power utilization down to zero, and you don't solve the problem. So no, the short answer is I take advantage of the full system. And you ask, does Apollo 4 have anything special? I would say that there's three things that I really like about Apollo 4. One is, as Scott was alluding to, using low power is super easy, right? Using our software. I can switch between high performance and low power modes, 192 and 96, without worrying about, did I save all my state, all this stuff. I just call a function, it goes to high power, I do my inference, and then I drop down to low. The same thing with deep sleep. I'm not a power expert, I'm an AI guy, right? So I don't want to worry about, did I put this peripheral in, this peripheral in, this peripheral? No, I just call deep sleep, it goes to sleep, and then the next interrupt wakes me up. Almost, from a firmware engineer, it's beautiful, it's wonderful to work with.
Yeah, that's a much easier than most of the situations I've had. I remember ourselves tying ourselves in knots at some manufacturers, trying to figure out how we were going to rate all of our firmware and APIs for our customers, and also make it capable of supporting all the different power domains and power modes that are available. So, like you say, to make it invisible to the embedded developer that it just the right power mode is selected as you're running along is a massive advantage. Now, one of the big things, obviously, about any type of AI machine learning application, it's about developing and training the model, and that can be a challenging process. And then once you've sort of figured out how it should work, which is typically done on a PC type performance platform, you then need to sort of shrink it and compress it and optimize it to run on a microcontroller. But often, the where you want to get the training data from, that's only something that you want to see how the data comes as the MCU sees it. So in terms of that, is there a way of sort of developing your AI model, but making use of the data that's being collected from the microcontroller?
Yeah, that is one of the very early problems that you run into when you transition from, say, the data center world, which is where I used to live, to the extreme embedded world. And so the first few models that we developed the hard way. You would do it on the laptop or on your GPU box. You would train on what you estimated to be the best data. You would do all the work to compress it, write some firmware around that to measure the performance on your MCU, collect that, and then go back and change your laptop environment, maybe change your compression or your quantization thresholds. So it's a very long iteration, error prone. Numerics are not the same in Python and on a Cortex M4. They're just not going to always match. The run times are different. So we developed a framework where we can make that evaluation board, what we call the EVB, a part of your laptop. It from Python's point of view, you're basically invoking a function, and that function is running on the EVB, and Python doesn't know. It just waits for that thing to come back. It's a remote procedure call, something that's very common in the data center world, but not so common in embedded. So we facilitated remote procedure calls for things like feature extraction. So maybe you're doing your FFT in Python because you don't care about that yet, and you're doing your inference on the EVB, or sometimes it's the other way around. Maybe you have a strange, you're computing quaternions in a very strange way for a kind of a motion detector, and it's just not matching. So your quaternions in Python are not the thing that you're computing on the EVB, and that's very common because very small numbers in your floating point environment will make a big difference.
Yeah.
So we have that facility to make Python easily compatible with the EVB. That's one of the ways we solve that problem.
So I mean, I think a lot of people are still sort of new to AI on microcontrollers in embedded systems. What's sort of been your experience of the environments that are available today? What's the best approach to having sort of a good experience with developing AI on a microcontroller?
So I think the industry has kind of gravitated towards TensorFlow, which is one of the AI frameworks. The reason for that is there's a good runtime. So when you train or when you run inference in TensorFlow, it's usually in the Python domain. Obviously, in a microcontroller, although there is a new Python that runs on a microcontroller, so it's a different topic. You can't run that same TensorFlow. So you're running it in an embedded runtime called TensorFlow Lite for microcontrollers. That's one of the more popular ones. It's limited. It doesn't do the same things that TensorFlow does. So you start learning, okay, don't do that. Like your doctor says, if it hurts, just stop doing that. If it doesn't work in TensorFlow Lite for microcontrollers, don't use it in your model. It turns out that doesn't always work, especially, I would say, in audio AI. Things that are processing audio are okay, classifying, understanding things that you say, like a keyword spotter. You can use TensorFlow Lite for microcontrollers. But if you're generating audio, a speech synthesis problem, for example, or a speech enhancement where you're taking speech and you're removing noise, the quantization that TensorFlow Lite for microcontrollers forces you to use, which is 8-bit, is too quantized. So you start hearing, because your ears are very, very susceptible. They're very sensitive to quantization noise. So we have to use 16-bit, and because it's not supported by TensorFlow, we actually had to write our own framework for that. So we have a specific framework for audio AI that's not TensorFlow. Right,
that's quite hardcore, I think. But as you say, if it's not there, it's not there, and an application like audio actually demands it, doesn't it? So a very challenging application approach. Now, one of the things I also noticed, and I had some experience with this in the past as well, is something called arrhythmia classification. Now, that's to do with monitoring the electrical signals related to the beat of the heart. And there are modules available on the market that you can buy where it's all sort of packaged into a chip, and you can integrate that into your application. And I think one of the problems is those signals are obviously very small. The sensors sort of stick onto your body but aren't necessarily always attached well enough. And it occurs to me that obviously the shape, we know what shape we're looking for, but the peaks aren't always as high every time, and the rise times can differ a bit. And to me, it seems like an ideal application for AI. You have got a project called HeartKit. Can you tell us a little bit more about how that came about, and sort of what challenges you faced in measuring and evaluating an electrocardiogram?
So, I mean, this is actually a great problem for endpoint. It's one of those beautiful problems, right? And, using AI to analyze your ECG on wrist or on body is actually a power problem. Because the traditional way to do it is you collect 40, 50 megabytes of data over, say, 30 seconds, and then you transmit that using Bluetooth. And as Scott was alluding to, that transmission, that radio is actually very power expensive. So the more compute you can do on the device, the less you need to transmit. So, and as you point out, noisy signals are, super hard to translate, to analyze. That's why you usually need a big model doing it back in a data center. So that's the other problem. And the beautiful thing is that that's what AI is for. Like, AI is hard, but it's the easiest way to do really hard things. You could write a million rules and DSP algorithms and everything to kind of figure out what signals are there and identify the peaks and all the shapes, or you could let AI do it. And that's what we've done with HeartKit. HeartKit was born because the person I hired, and I didn't know this at the time, that was his PhD. He had done his dissertation on ECG analysis and endpoint devices. So after like a couple of weeks of him working on an audio problem, he goes like, I could do ECG. It's like, yes, you could. So I took advantage of that situation. And the bottom line is we can do full heart analysis, not just AFib. We can detect things like QPRS. I don't know. He's the expert. We can detect all kinds of features about the heart and not transmit all that data. And it doesn't have to be ECG. Turns out that a lot of that signal, a lot of that information can be picked up using optical signals as well. So PPG, and that's coming. We're adding that to HeartKit very soon.
Yeah, it sounds fascinating. I worked at a company for a while where we were doing sort of heart monitoring as part of a heart massage support system, still in development, and it's partially implanted in the body. But that was, I sat there and worked my way through that 2/3 section of the alphabet, going through all the peaks and troughs and rise times from through. So it's a huge learning experience as to what can be done. So we're coming towards the end of the show. I want to pull Scott in as well, just so as we can have a bit of a round table discussion around a few topics. If you do have any questions for our audience, I know you're out there. I can see you're watching and joining us. If you've got any questions around subthreshold technology, the spot technology that Ambiq uses, or AI in low power applications, feel free to drop in some questions. I've got a couple of other bits and pieces on my list here, and one of the things one of the areas where I've been active in the past is in debugging, and debugging is notoriously complicated in situations where the microcontroller's clock is turned off for any reason or parts of the system are shut down. What's the sort of like the Ambiq debugging environment, and how do you manage to maintain a debugging session with the microcontroller potentially going offline and sleeping?
So it's a pretty standard debug environment. Carlos, in fact, you're the consumer, you're the user of this, so maybe you're best to speak to your experience with it.
Yeah, I debug all the time. So
I hope so.
it's boringly standard. So we I use GDB to figure out things like site faults and all that, and that works right through it doesn't even know about deep sleep. So that's fine. And then we use a couple of profiling and kind of debug things called the ETM, event trace monitor.
Yeah.
Embedded trace macro.
That. Which is great for performance and figuring out, it turns out, as I was mentioning, TensorFlow Lite for microcontrollers, not great. It's good, it works, but when you turn on, ETM and you're looking at what TensorFlow actually does, you're spending more time doing adds. So, Tensor A plus Tensor B, and less time doing max. The max are super, the multiply and accumulates, very optimized. They forgot to optimize the adds. So things like that is where it's not just debugging, it's also being obsessed about power and obsessed about performance.
Yeah.
And in fact, that brings up a good point. Is debug is not just functional debug, right? It's power debug, and so we've put a lot of thought into that. There are as Carlos just alluded to, we do a lot of profiling. So we try and figure out what are the cache hit and miss ratios. Some of the newer Ambiq products that are unreleased have some even further developments on that front to give us even more sophisticated analytics. And then we have a whole set of registers on board where you can quickly probe to see, well, what clocks are active, what power domains are active, and so forth. And we try to make it easy for our customers to access that. But definitely, this is a point of great challenge with customers. And oftentimes, we're having to sit there with them and teach them how to do the power debug properly.
Yeah. And in terms of development environment, I mean, there's lots of different approaches. Some people have their own that they supply. There's obviously others like IAR and Sega that offer a development environment and debug hardware. What's the best way to get an IDE up and running and a debug tool with an Ambiq microcontroller?
Carlos, I'll let you speak to that one too.
We use everything and we support everything. So some of our customers use IAR. We support that in our basic toolkit Ambiq suite. And also Kyle. I personally prefer using Visual Studio. I think that's more standard across the industry nowadays. And it has a bunch of tools for Cortex-M devices and hooking up GDB and all that. All just kind of flows very nicely.
Now, in terms of sort of markets, just to get an idea of sort of where you're seeing the most low power applications, is it in sort of wearable medical at the minute, or are there some others that are sort of popping up that you sort of surprised you?
Well, I would say from my perspective, wearable medical is where the lion's share of our focus is today. We have a lot of consumer wearable devices. We're spending a lot of time there. But what is called a medical device and what is called a consumer wearable is quickly kind of blending together, right? A lot of our consumer wearables companies are getting to be more medical in nature, and then we're having a lot of more traditional medical companies that are launching things that look something like a consumer wearable device. So yes, that's a big one. I am particularly excited about, let's call it smart home and smart factory type applications or smart industrial type applications. We're seeing there, it's the breadth of opportunity that's available is staggering. And that's the thing that overwhelms me. I get excited because I want to go after this one and this one and this one. And so, what we do as an executive team is we sit here and go, okay, let's find commonality among the largest subset of these things that we can get after. It turns out it's not so much the hardware that's the issue, it's software, right? Our customers probably spend, I'm going to say that 90% of our engagement with our customers is around the software. It's do you have the right drivers? Do you support the right peripherals? Do you support the right radio protocol for this particular use case? And that's where we're spending our time, not so much on the hardware side of things. And so to serve new markets like that generally requires new software. So like I said, I'm excited about all the wealth of opportunity in smart home and smart industrial. And Carlos has kind of a different view on things. So I want to hear his perspective as the AI guy here.
I mean, in terms of, feeling good about yourself and helping the planet, I think remote patient monitoring is where it's at. We're just scratching the surface. There are AIs that can listen to you and tell you, hey, you may have a touch of dementia. And we're laughing about this, but the demographics are changing. Like, we're not going to have enough doctors soon. And having a monitor that says, hey, you may want to talk to your doctor about X or Y, or there's another model that we were looking at that detects, we already have a model that detects fitness. Are you running? Are you walking? Well, this model will tell you your gait is off. Like, you're walking too much on one foot, or you're not putting your weight down right. Maybe you have what we call Parkinson's gait. So the applications in the medical world are not just like commercially really attractive because we're all going to need something like this. They're also like super fulfilling, right? You're really helping people. Like even something as simple as detecting that somebody fell can change somebody's life.
Yeah. Now, obviously, the microcontroller is typically the largest part of most applications because that's where the intelligence is, that's where the flexibility is. But do you also see a need for either yourselves or maybe for other sort of partners in the industry to be innovating more in terms of things like energy harvesting, battery technology, and supercapacitors and things like that?
Yeah, absolutely. We laugh internally because zero is the only power level that is kind of deemed acceptable, right? If the engineers come to me and say, Scott, we found a wonderful way to get down to this workload at 10 microwatts, I'm going to say, well, why isn't it 5 microwatts, right? And zero is the only acceptable number. And yeah, you're right. There's other components in these systems, whether it's MEM sensors, microphones and this sort of thing, or it's the power conversion circuitry. That all needs to be attacked. Good news is I see this as an important problem that a lot of companies are getting after. Companies like us are sucking in more of these components on board. So we have our own voltage regulators on board. It's only a matter of time before things like energy harvesting get pulled in as well. Frankly, I'm waiting for the right customer to just tell me we really need this and now, right? Because we have so many demands of our time. We're just waiting for the right customer to come along. So if that customer is listening today, let us know. We want to know. I'd love to pull in energy harvesting circuitry. But yes, in short, yes, I think we as a community, there's a great low power community out there. We're all attacking these problems. There's a need to do so. And so, again, to your listeners, you need to flag the things that are problems for you and bring them to our attention. We have got really smart engineers, whether it's a software problem that Carlos can attack or it's a hardware problem that I can attack. We're fanatical about attacking every last picojoule.
Well, you're in luck today because I was going to end the show, but we've just got a couple of questions to come in. So let's see what we can do with these. Philip Ling, an ex-colleague of mine, is joining us from LinkedIn, and he has got a couple of questions. So I'll split it into two. The first one is, can Spot go beyond embedded IoT to tackle the power challenges of running AI in data centers? What do you think about that?
Yeah, absolutely. Yeah, we get asked by our board of directors all the time this same question, and the short answer is yes, absolutely. As I mentioned earlier, well, let me back up. The chief challenge with Subthreshold, in addition to all that process variation, is also that it's slower, right? I can't run a Subthreshold processor at 2 gigahertz, but with neural networks, with inference, or with training, we're talking highly parallel operations, so I can go wide. I don't have to go high speed in order to achieve big throughput. And so if I adopt that approach, then yes, indeed, we can apply spot and near threshold and subthreshold computing to AI computations in the data center. And as Carlos talked about earlier, total cost of ownership and power consumption in particular are major considerations for the data center owners. So yeah, it's an opportunity for sure. Super.
And then the other question which Philip brought up was also, it sounds like high performance computing is going to be big in automotive. Will or are your microcontrollers be qualified for automotive applications? And I think also just in the vehicle in general, we see this new architecture where there's radar sensors and ultrasonic sensors and everything possible sort of spread around the vehicle, and they're looking at reducing power for electricity consumption from the battery. Is that something you can cover as well at the minute?
We are, I'm going to say that support for automotive is something that is on the roadmap, the farther out roadmap, but it's not today. There's nothing fundamental about the technology that precludes us from attacking that. It's just a matter of, as a company, we have to make sure that we're ready to get after that. There's some major constraints around silicon that's going to be in safety critical systems. So we will get there. The technology is amenable to going there, and it just is going to take a little bit of time.
Yeah, super. Well, thank you ever so much, Scott and Carlos, for joining us and providing so much information. I think you both get the feeling we could probably do another hour of this and still not all the questions answered. So it's been great fun. I've really enjoyed chatting to the pair of you. Thank you.
Thanks for having us.
It was a blast. Thank you.
So that's unfortunately all we have time for in this episode. So what did we learn? While the big guys all argue about who should run ChatGPT and whether the world will collapse in on itself because of generative AI, we run the risk of overlooking AI operating at the edge in microcontrollers. Almost all engineers have faced a task that is beyond the realm of procedural programming, and AI can be the solution. This is because many of today's challenges require better data, collected more consistently and in locations that are challenging to reach or where power sources need it to be small and light. As we've seen today, it's clear that medical is one key area that could benefit hugely from improved diagnostics data collection. Now, to achieve this, we need programmable systems like microcontrollers that are very economical with energy, but also offer enough performance for the task at hand. Subthreshold operation, as offered by Ambiq, is definitely a technology worth exploring if you're tackling a low power and AI application. My thanks go out to today's experts, Scott Hanson and Carlos Morales from Ambiq Micro. You've delivered us with some outstanding engineering insights. So that wraps it up for today. If you'd like more of the same, we're broadcasting 2 episodes of Engineering Insights every month in 2023. And to keep you abreast of industry trends this year, take a look at News Bites, our monthly 15-minute show. Please like, subscribe to Elektor TV Industry on YouTube and share our videos on whatever platforms you use. Additionally, you can now drop by the website at elektormagazine.com/EEI to see the topics for future shows and sign up for regular updates and reminders. Finally, if you'd like to join me as a guest, write me an email, drop me a tweet, or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining, stay in touch, and don't forget to keep asking your engineering questions.